Hello, everybody, and welcome to the Latin American webinar of physics, or of physics for short. So welcome everybody for this very nice webinar that we are going to have today. Remember, for all the people that is following us in the different social network, that you can connect and subscribe to this YouTube channel, and then you can see all the previous webinar and to keep updated with the latest things that are happening in physics about research and other topics like astroparticles, particles, etc. So this time we have a very nice talk because Christoph Ternes, he is from the Istituto Nazionale di Fisica Nucleare in Torino, the INFN-Sezione Torino. So he's going to talk about phenomenology of sterile neutrinos, but before just a little bit presentation, he obtained a PhD in the Instituto de Física Corpuscular in Valencia in Spain, and now he's postdoc in the INFN in Torino. So Christoph, welcome to lawphysics, and you can share your screen and start whenever you want.
Okay, can you see my screen now?
Yes, we can see it.
Okay, good. So thank you, Roberto, for the introduction. So today I will talk about basically about neutrino oscillations, and in particular about neutrino oscillations in presence of light and heavy sterile neutrinos. So neutrinos are produced at some source in charged current interactions as weak states like here. So they can be, the weak states can be written as superpositions of mass eigenstates, which are weighted with the entries of the lepton mixing matrix U here. So in the propagation, the mass states evolve in this form here. So from here, we can trivially obtain the evolution of the flavor states by just substituting nu k of t here for nu k. So this means that a neutrino, which is initially produced as nu alpha, will have some different composition after some time t. So then when arriving at the detector, the neutrino, which was initially alpha, has a probability to be detected in a different flavor, nu beta. So the transition probability from nu alpha to nu beta, so the transition amplitude is given by this quantity here. And from this, we can obtain the oscillation probability by taking the absolute value squared of this. So in the standard case, the mixing matrix here, which characterizes the oscillations, is written in terms of three rotations, which are characterized by the three mixing angles here, theta 1, 2, theta 1, 3, and theta 2, 3. The 1, 3 rotation here also has the Dirac CP phase associated with the mixing angle 1, 3 here. Actually, there is a fourth matrix to the right here, which contains two more CP phases, which are the Majorana phases. And I have not written them down here because they actually do not appear in the neutrino oscillation probability. So oscillation experiments are blind to Majorana CP phases. We have three massive neutrinos, which can be arranged in two different forms. So in the first form here, we have nu1, which is the neutrino with the largest electron content, is the lightest neutrino, followed by nu2 and nu3. And alternatively, nu3 can be the lightest neutrino, followed by nu1 and then nu2. So in the first case, we talk about normal neutrino mass ordering, and in the second case, we talk about inverted neutrino mass ordering. Now, in any case, oscillation experiments cannot measure directly the masses themselves, but only mass squared differences. So these are the deltas here. So delta m31 squared is m3 squared minus m1 squared, and so for the delta m21 squared. So you see that for normal ordering, this quantity delta m31 squared is positive, and for inverted ordering, delta m31 squared is negative. Okay. So we have a total of 6 oscillation parameters. So the two independent mass splittings and the 4 quantities here, which define the lepton mixing matrix U. Now, over the last 20 or more years, all of these parameters have been measured more or less well. For example, the delta M21 squared mass splitting has been measured principally by the Kamland long baseline reactor experiment. The other mass splitting, or the absolute value of this mass splitting, has been measured by long baseline accelerator experiments, atmospheric experiments, and also reactor experiments, and so on here. So you see that any of the parameters is measured by at least one class of experiments, sometimes even more classes of experiments. There is no parameter which is measured by only one experiment on their own, except for the case of Kamland here for the first one. So this means that if we perform a combined analysis of all of the neutrino oscillation data, we will get more stringent results on the allowed ranges of the oscillation parameters than from an analysis of a single experiment on their own. So this is the good motivation to perform a global analysis of neutrino oscillation data. Now, if we do this, as we have done, for example, in this paper here, we get in the single analysis of the experiments these regions here. So this is a bit simplified because many of the parameters measure more, many of the experiments measure more than only two parameters. But so this is basically a recompilation of the data that we have included in this global fit. So for the reactor experiments, we use data from Reno and Daya Bay. For the accelerator, long baseline accelerator experiments, we have Ninos, T2K Nova. For atmospheric experiments, Ice Cube, Deep Core, and Super Kamiokande. And also data from the long baseline reactor experiment Kamland, and all of the solar data which has been collected so far. Now, if you combine all of these data sets, you will eventually get some profiles like these ones here. And essentially, as of now, the angle theta 1, 2, the mass splitting delta M21 squared, and the angle theta 1, 3 are measured very well. For the remaining three here, we have basically the last unknowns in the standard neutrino oscillation picture. So for the atmospheric angle sine squared theta 2, 3, we don't know if the value is larger or smaller than 0.5. And this is sometimes referred to as the atmospheric octant problem. So right now you see that the best fit is in the second octant, but first octant solutions still remain allowed at more or less 2 sigma confidence level. Another unknown is the value of the CP phase. So you see we are obtaining this profile here, but actually there are only two measurements, one from T2K and one from NOVA, and they disagree. So the T2K best fit is actually like so close to 1.5, and the NOVA best fit is somewhere here close to 0.8, and then in the combination they meet somewhere in the middle. So we don't know what is going on here. So the second unknown is the value of the CP phase. And the last unknown is the neutrino mass ordering. So here in these plots, in blue is the result for inverted ordering, and in magenta, the result for inverted neutrino mass ordering. So you see it is always like 2.5 sigma above the normal ordering. But these 2.5 sigma actually do not come from a single measurement of an experiment on their own or so, but they come like from a series of tensions which are small or large in determination of the remaining parameters. So we still don't know what the real neutrino mass ordering, if it is normal or inverted. These profiles, which I have here shown, can also be translated into numbers. And from this table, you see that all of the parameters, except for the CP phase, are currently at the below 5% precision level. Okay, so now all of this picture seems very complete, and to be functioning, there have been several observations which cannot be explained with three neutrino oscillations. So first, in this plot here, we have what is known as the reactor antineutrino anomaly. So we have plotted here the ratio of observed and to calculated events. And you see that for most of the reactors, indicated by the different points here, it is actually below 1, what you would expect. And if you take the average of all of the measurements, you see that you are actually around 3 sigma away from unity. So this is a 3 sigma effect. And the second one is the gallium anomaly, which is depicted here, and something very similar is happening here than in the case of the reactor neutrinos. So in the gallium experiments were actually used to measure solar neutrinos, but in the calibration phases, they were exposed to strong sources of electron neutrinos. And again, we have found that, or someone found that there was about 3 sigma deficit in the ratio of observed to calculated events. So you see that this is a second 3 sigma effect here. And the last one was an excess of events in the LSND experiment. So LSND was looking for, was using a muon neutrino beam, and they were expecting basically this background here of electron neutrinos or antineutrinos. And the dots here are what they actually observed. So you see that here they have a large excess, actually at close to 4 sigma level, excess of antineutrino events. Okay, so these anomalies cannot be explained with these parameters which we had here, because you see that the mass splittings which were obtained from this global analysis are at the order of 10 to the minus 5 and 10 to the minus 3 here. So if you calculate the oscillation lengths which are corresponding to these values, you see that the 2-1 oscillations occur at about 50 kilometers for one mega electron volt, and the 3-1 oscillations occur for about 1 kilometer. So, however, actually here the gallium sources, they were only about 2 meters from the sources. The reactors you see that is plotted here on the x-axis, they go from like 10 to 100 or so. So also very short baselines are included here. And also the LSND experiment had a baseline of about 30 meters. So if you take the L over E ratio, which is corresponding to these experiments, you actually need a new mass splitting, which is at the order of 0.1 electron volt squared. No, so in order to accommodate this in the neutrino oscillation picture, we need a fourth neutrino. So we can extend the 3x3 neutrino oscillation lepton mixing matrix to a 4x4 matrix. So now, so S stands for sterile, because the fourth neutrino cannot be an active neutrino. So it means it is sterile neutrino in the sense that it cannot participate in weak interactions. So now having this extended mixing matrix and the new mass splittings, we will have new disappearance and new appearance channels. So in the disappearance channels, our effective mixing angle, so the effective amplitude of our short baseline oscillations depends on one of the new U entries, while for the appearance channel, the effective mixing angle depends on 2 of the U entries. Actually, you see that in the disappearance channel, the U entry is entering, so the U alpha 4 entry is entering linearly, while here it is entering quadratically. So you assume that the appearance channel should be quadratically suppressed if you assume that your extended 3+1 matrix is like an effective correction to the 3x3 matrix. Now, the appearance channels are important for the LSND experiment that I have discussed before, and also for experiments like Carmen, Miniboon, Opera, and others. While this appearance channel for PEE, we have the reactors and the gallium experiments, and for atmospheric experiments and accelerators, we have we can also look at the P mu mu channel. So now if we perform an analysis of the data from the gallium anomaly, reactor anomaly, LSND, you will see that indeed the preferred mass splittings are at the order of at least 10 to the minus 1 electron volt squared. Okay, so here you see also that actually the mass splittings coincide for the gallium and reactor anomalies. So now this has been some time ago, and the reactor neutrino anomaly had to be tested. The problem with the reactor antineutrino anomaly is that it depends directly on the flux prediction from the nuclear reactor, and there are several models which can differ a bit one from another. So depending on the model that you choose, your reactor antineutrino anomaly can also get modified. So in order to overcome this flaw from the reactor antineutrino anomaly, new experiments were designed where instead of measuring the total rate, they measure the ratios with the detector put at different distances from the source. So for example, here we have like a cartoon of Dan's experiment where the detector can be lifted to different positions. So then instead of taking the rates at one position, they use the ratios at, so actually in Dan's it can be put to 3 different positions. So you can make 3 different ratios out of that. So the analysis is performed taking the ratio of the detector to the respective positions. So in this case, you basically cancel the effect from your reactor flux model uncertainties. And indeed, when the combined analysis of Dan's and Ninos data was performed in 2018, there was a more than 3 sigma preference in favor of sterile oscillations, as can be seen here in the left figure. So you see that both experiments had individual preferences or about 2 sigma level in favor of sterile oscillations. And then when combining, this was increased to more than 3 sigma. So the mixing angle that they obtained here, it was a little bit smaller than the preferred angle from the reactor antineutrino anomaly, but still at 3 sigma, you see that there was complete overlap between both measurements. So, however, this was 2018, and then Dan's released new data in 2019, and this preference actually went down. So there was less agreement between the analysis in this new data set, and you see now there were no closed 3 sigma regions anymore. So still at 2 sigma, you had closed intervals. So the preference was above 2 sigma, but not as large as it used to be in 2018. And now the Dan's collaboration has released also new results and also some of the other experiments. And actually the picture has changed even more because using more recent data or most recent data, you see that there is actually no preference anymore, not even as 2 sigma. So you see that the regions here in green, they go back to 0. So we have no closed contours anymore at 2 sigma. Still at 1 sigma, but the large preference that was observed in 2018 is mostly gone. So then the only thing that can be done with this data is basically put upper limits on the UE4 entry of the extended mixing matrix. But of course, this was not including neutrino 4 data, because then we have this very, let's say, huge result where they actually say that they observe sterile neutrino oscillations at more than 3 sigma confidence level on their own, so without the need of combination with any other data sets or so. But the thing is that the mixing angle that they obtained, so here you see that the crosses in blue and black are the data, and the red dots are the best fit prediction from the experiment. So you can see the oscillation even if you look only at the data, right? So the problem is that the mixing angle that they obtain is very large. It is actually so large that you could not even say anymore that your 3+1 case is just an effective correction to the neutrino oscillation. And also the mixing that they obtain is in tension with other data, as for example indicated here with solar experiments. So the neutrino 4 collaboration measures the ratios between 24 different distances. So they take here 24 different distances and average them and take the ratio to the average at all other distances. And also they use 9 energy bins. So they have basically 24 distance and 9 energy bins. Now, in order to create a figure like this here, they group all this independent distance and energy bins into bins of L/E. Okay, so this is how you get from the independent distance and energy bins to bins in L/E. So this is basically what they observe, and then when you want to make the analysis, this is how you calculate the number of events for these ratios. Okay, so basically you see that we have to take the average over the oscillating term here. Now this average is calculated in this form here, and I will not go into detail, but this basically just contains several detector reactor effects and also an averaging over the distance of the reactor, which is important for short baseline oscillations. And in particular, it contains the resolution function of the reactor. Now, using the information which was provided by the neutrino 4 collaboration in this paper here, we can actually extract the energy resolution function, and it is given in this form here. So we use Gaussian energy smearing with this resolution here. So if we perform the analysis, then comparing our predicted event spectra with the observed events, we get the red, magenta, blue lines here. So you see that we actually obtain in our analysis a value of the mixing angle which is even larger than the one from the neutrino 4 collaboration. So it is actually maximal. But on the other side, we obtain open 3 sigma bounds. So we don't have a 3 sigma preference. It is below 3 sigma, but still above 2 sigma. The only way that we were able to reproduce the results from the neutrino 4 collaboration was by ignoring the energy resolution of the detector. If we do this, we get here the yellow-green lines, which are in good agreement with the results, official results from the collaboration. In any case, here we have still plotted also bounds, for example, from Catherine, from solar data, and from other ratio experiments, prospect and stereo. So you see, even in the official results, they are in strong tension with the results from these other reactor experiments. Now, in this analysis here, we have used the standard chi-square analysis, which does not take into account possible fluctuations in the data. Now, if we repeat basically this exercise, but taking into account these fluctuations, the preference is further decreased. So here we show now on the left side without energy resolution, on the right side with energy resolution, how the preference goes further down. So the dotted lines are the same as before, corresponding to the standard chi-square analysis. And now the solid lines are the result from this Monte Carlo analysis, taking into account statistical fluctuations. And you see that also in this case here, without energy resolution, we do not obtain closed 3 sigma confidence regions anymore. So for the summary of this neutrino 4 analysis is basically that if you start without energy resolution and performing the standard chi-square analysis, you obtain a preference at the 3.2 sigma level. However, after adding, as should be done, the energy resolution and also performing the Monte Carlo analysis, the preference is reduced to only 2.2 sigma. So the results that I have shown you correspond to this 500 keV data, but the neutrino 4 collaboration also presented different analysis using like an average of different data points, which I did not show you, but essentially the analysis is the same. So it goes from a 2.7 initial preference to a 2.2 final preference. Okay, so you see that in the other ratio analysis, we don't have a preference for sterile oscillations anymore. And for the neutrino 4 analysis, we have a result which is, or they obtain a result which is rather doubtful. So we can also now see what is going on in different oscillation channels. Sorry, no. So there's one more thing that I wanted to show you about neutrino 4. We have created at the order of 100,000 neutrino 4-like data sets without including oscillations, and performed an oscillation analysis of this unoscillated data. And here I have plotted the best fit distribution obtained in these analyses. So you see that for a neutrino 4-like experiment, there is always a large probability to find a best fit value with very large mixing, even in the absence of oscillations. Okay, so this is true for both cases, without the energy resolution and including the energy resolution. So regarding the other channels than the electron neutrino disappearance, there were also searches with muon neutrinos, and there was no evidence found in favor of 3+1 oscillations. So you see that here on the left side, we have the exclusion curves from many experiments. So basically everything which is on the right from each line is excluded at 3 sigma confidence level. And from the combined analysis of all data, we obtain the red line here. Do you see the driving force in this determination here for U mu4 is basically Ninos plus, which is the blue line here for low masses, while for large masses, there are contributions from more experiments also important. Regarding the last of the sterile matrix elements, U tau 4, actually the strongest bounds come from atmospheric data. So last year, there was also an update on this figure, because last year, IceCube released this analysis here, where they used 8 years of data. And you see that now actually they obtain a closed region at 90% confidence level. So you see, it is not very significant, but still it is a closed region. And interestingly, it actually coincides exactly with the mass range, which is important for the reactor antineutrino anomaly, or also experiments such as neutrino 4. So these data here are not included in this figure because they have not been made public yet. So once they are public, we can also make the combined analysis to see how large this effect can be in comparison with the other experiments. So this is so much for disappearance experiments, but of course we also have the appearance experiments. And especially there was a large preference in favor of oscillations in LSND and mini-boon. So you see they are here painted in blue and red respectively. And although both of them have observed excess of events, you see that they only partially agree with each other. In particular, is interesting is that most of the mini-boon region is actually excluded by Icarus and Opera, which are the vertical lines here. So you see only the upper part of the region here survives. In the case of LSND, we have the lower region here and the large regions here. So the large region here is also there for mini-boon, but at larger confidence levels. But these regions are cut off by other experiments, such as, for example, Carmen and Nomad. So if you perform the combined analysis of all of these data, you get, again, closed contours at 3 sigma confidence level. So this raises the question if a global fit in the 3+1 picture is a sensitive thing to do. So you see that the disappearance experiments measure UE4 and U-mu4 for electron neutrino experiments and mu neutrino experiments respectively, while the appearance experiments from the last slide here, they measure the effective mixing angle, which depends directly on both of these quantities. So if you combine the electron and the mu on disappearance experiments, you can also bound this mixing angle here. And for example, this has been done here in 2017. In blue, we have the combined analysis of all appearance data, and in red, the combined analysis of all disappearance data. And you see there was a nice overlap in this region here, roughly above 1 electron volt squared. And again, closed regions at 3 sigma confidence. So since then, many new data have appeared. So if we make like a more or less up-to-date version of this figure, it looks like this. So you see that the appearance and disappearance regions are fully disconnected. So this means that the global 3+1 neutrino oscillation fit is statistically not acceptable. So the goodness of fit obtained here is at the level of 10 to minus 11. So you see basically the message here is that we still don't know what is going on, because we have a very large significant observation of excess in mini Boone and LSND. We have the reactor antineutrino anomaly, which is still there. The ratio anomaly is mostly gone, but still we have the neutrino 4 data. So basically, this will probably remain a very active field of research in the next years. So this is all I wanted to tell you about light sterile neutrinos. Now, in the last part, we go to heavy sterile neutrinos, which are predicted or required in type 1 seesaw mechanisms. Okay, so in this case, our lepton mixing matrix is extended into this form here. So we have N, which is a 3 by 3 matrix, which is describing the lepton mixing for the light neutrinos. But now we have also S, V, and T, which contain the mixing between active and sterile neutrinos for S and V, and the mixing between sterile neutrinos in the case of T. Okay, so this means that the submatrix here, which is describing neutrino mixing in the light sector, is not unitary anymore. And it was shown that a convenient way to parameterize this matrix is by just taking the standard 3 by 3 matrix that we had before. So this is the standard PMNS matrix, and it is multiplied with this triangular matrix, which basically contains the deviation from unitarity. So in this case, we have 9 new parameters in neutrino oscillations, because the diagonal parameters here are real, but the non-diagonal parameters can be complex. So you see that we also are including here new sources of CP violation in neutrino mixing, which also can be highly degenerated with the standard CP phase, as shown in this figure, which I have taken from this picture. Okay. Now, if the new neutrinos, the heavy neutrinos, if they are very, very heavy, they are very, very strong bounds from electroweak measurements. So you see that then the bounds on the alpha parameters are going to the 10 to the minus 3 level. If we have lighter neutrinos, these bounds are relaxed, and then actually bounds can be derived from neutrino oscillation experiments. So I say lighter here, but I mean lighter with respect to the electroweak scale. They still have to be much heavier than the light sterile neutrinos that we have discussed before. Okay, so in this case, neutrino oscillation probabilities are modified in this way. So for the p mu mu probability, we have the standard probability, which is multiplied by one of the alphas here. And we have also new terms, which contain also the new CP phases here. And also the appearance probability gets modified in this way. So you see that again, the standard term gets this prefactor, while a new term appears containing both phases. And now we also have actually a zero distance effect term here. So you see that this last term, it does not depend on the energy or the baseline anymore. So this means that the zero distance flavor transformation is possible in this scenario. So we have performed combined analysis of short and long baseline data using this non-unitary parameterization of the mixing matrix. And we have used short baseline data from NOMAD and NUTEF experiments and long baseline experiments T2K and NOVA. Okay, so from our analysis of NOMAD and NUTEF, we can put rather strong bounds on the P mu E oscillation probability here. So this is the combination of these parameters at a level of like 5 or 6 times 10 to the minus 4. In the next step, we will combine this result here with the result from long baseline data, and we can do this by just transforming this chi-square here into a chi-square of alpha 1 1 and the absolute value of alpha 2 1. So if we do this and project the result from our analysis into this plane where we have minimized over all of the other parameters, so all of the standard oscillation parameters and alpha 1 1, we obtain these contours here. And so you see that basically the bound on alpha 2 1 is more driven from the short baseline experiments, and the bound on alpha 2 2 is mostly coming from long baseline experiments. You see that the T2K, the combination of T2K and short baseline data can put a much stronger bound on alpha 2 2 than the combination of NOVA and short baseline data. And this is because because in the standard analysis, T2K has a better determination of the mixing angle theta to 3, which is basically the principal factor in the standard oscillation probability here. So you see it will be directly correlated with the new parameter alpha 2 2. So therefore, a better determination of theta to 3 translates on a better determination of alpha 2 2 in this scenario. So when we project this into the one-dimensional plane, we can obtain these bounds here on the alpha parameters. Now, these bounds can also be translated into bounds on the unitarity of the mixing matrix directly. So there are different parameterizations for this 3x3 matrix. So we have used here this triangular form of the matrix, which is multiplied on the standard matrix, but there are different parameterizations, for example, using Hermitian matrices. So the idea of this is to translate the bounds of the alphas in a general bound, which is not depending on the parameterization of the non-unitarity that has been chosen. Okay, so I have also said that there are new sources of CP violation in this non-unitary scenario, and it would be good to see if they can ease this tension that I have talked about a little bit in the beginning between T2K and NOVA data. So basically, these are the result from an analysis of T2K and NOVA data, where you see that T2K prefers values of data close to 1.5 pi, while NOVA is living here in the second region. So they basically perfectly disagree with each other. So the idea was to see if, due to these new correlations, there can be some central value found for the phases, and that this tension might go away. But unfortunately, it does not go away, because you see here in blue the region obtained from the analysis of T2K data, and in red, the analysis for nova data, and they perfectly disagree with each other again. So this is for the alpha parameters hold down at the best fit value that we had obtained, which is very close to unitarity. But this remains true also if you allow values which are further away from the unitary point. So you see that here the nova region starts to close in the region around 1.5 pi and 1.5 pi, but the T2K region starts to open up. If you go to even larger values, they still avoid each other. And if you go even to rather large, maybe already at the boundary of the allowed region values, this is still true. So you see that when including these new sources of CP violation, the T2K nova tension is not going away. Okay, so this brings me to the conclusions. So we have seen that some of the oscillation parameters, basically sine squared theta 1, 2, sine squared theta 1, 3, and delta M2 squared, are rather well measured, but we still have open issues regarding CP violation, the octant of the atmospheric angle, and the neutrino mass ordering in the case of standard neutrino oscillations. For 3+1 mixing, so light sterile neutrinos, we see that there is no preference anymore in the ratio analysis of reactor experiments, with the only exception of neutrino 4, where the result is more or less doubtful. We have also seen that the global fit to 3+1 oscillation data is not possible at the moment due to these very strong tensions which appear between appearance and disappearance experiments. But on the right side, we have seen that neutrino oscillation experiments can be used to constrain heavy neutrino mixing, but unfortunately the CP tension observed in T2K and nova can not be resolved using these heavy neutrinos. Thanks.
Thank you very much, Christoph. It was very nice webinar about all the different features of sterile neutrinos. So just for the people that is following the live transmission, don't forget to, if you like this webinar cycle, you can subscribe to the YouTube channel, as well as you can check our social networks, and maybe also to subscribe to the mailing list in order to receive all the notification and to be updated with all the activities that we are doing here in lawphysics. So let's start with some questions. Let me just check because for the people that is following us in YouTube, you can write the questions or your doubts or comment in the YouTube live, in the chat, in the YouTube transmissions. So maybe we can start with some questions here from the audience. Meanwhile, we give some time to the people to write questions there. So is somebody want to make a question for Christoph here in the audience? Okay, I have one question. I mean, I have many questions, but when you were talking about the CP phase, is usually assume, I mean, is there any capability or physical implication for the CP phase in the sterile neutrino sector? I mean, with this fourth neutrino, like, do you expect to have more phases than the typical delta from the three neutrinos?
Yes. So in the 3+1 case, you have actually also two more CP phases, but they are not relevant for the reactor experiments. So they would only be relevant also for experiments which measure electron neutrino appearance at very large baselines. And actually then you can also have cancellations among the new phases and the standard phases.
Okay, and well, for the moment there is a question from Joel that I'm going to ask you, but before there is greetings that Jorge Terol, he's saying, nice talk, Christoph. He's saying some.
Thank you.
So let's see. I mean, Joel, he sent a question via the chat because he has some connection issues, but he's asking on slide 29, you present an updated 3+1 fit. What spoils the fit? One specific experiment? Can it improve by removing something?
Yes, it can be improved by removing mini-Boon and LSND, because then you have no lower bound so you see that the only lower bound coming on this quantity sine square 2 times theta mu e or e mu is from LSND and mini-Boon. So if you remove these two, it can go back. It can go to any value like to 0. So then this region here will extend also to 0, and then you will have overlap in this region. But so in this 2017-18 fits, it was possible to very strongly improve the goodness of fit by removing, for example, only LSND or mini-Boon. But this is not possible anymore. So if you include either LSND or if you exclude either LSND or mini-Boon, it is still, the goodness of it is still really bad. I mean, better than here, but still not good. So you have to exclude one full class of experiments.
Okay, so it seems that there is a, no, Joel is saying thanks. Okay, so there is a, maybe there are other questions here, or it seems that. Okay, I have one question that also I got a little bit confused now. There is a question from David Vanegas. He's asking, what is the future of the 3+1 model? Can we say that it is ruled out by current data?
No, so I mean, we can say that the combined explanation of LSND, mini-Boon, and reactor antineutrino anomaly is very unlikely. But I mean, the mini-Boon and LSND are experiments which have an excess of 4 and 5 sigma confidence level, right? So this is something that cannot be ignored. We just have probably, this is not the right explanation, or maybe not, but the excess is there. So it needs an explanation, and we have not found it yet. And also, I have said that the ratio analysis are now, so from all experiments except neutrino 4, the ratio analysis are not preferring 3+1 oscillations anymore, but we still have the gallium and the reactor antineutrino anomalies. So they are not gone, they are still there as well.
Okay, so there is another question via this time. Martin Young he sent the answer, the question. He is asking, are you saying that the neutrino 4 experiment is not suited for do what they tried to do? The plot with the assumption of no oscillation is basically saying that they can expect fake signals, but how it is not included in the experimental analysis by the collaboration?
Yeah, so to basically include this, one needs to make the Monte Carlo analysis, including the statistical fluctuations of the data. And this has not been done by the neutrino 4 collaboration yet.
Okay, so maybe I have another doubt. I mean, because now I got a little bit confused. What is the essential difference between these two experiments that give so different results? I mean, mini-Boon and LSND, is the technology that they used, or the type of target, or?
No, the results from LSND and mini-Boon are more or less in agreement, right? So they both observe an excess in the electron appearance channels, or antineutrino electron appearance channels. So the problem is that the mixing angle that they need to explain this excess is very large, you see? So here it is at the order of 10 to the minus 2. But if you make now the combined analysis, so you have a bound on U mu on UE4 and then U mu4 coming from the muon experiments and the electron experiments. Now, using the bound that you get from the reactors, for example, on this one, and from IceCube, Ninos, etc., on this one, you can construct bound on the combination of these two. Okay, And so this is how you get the red line here. And you see that the combination of the bound that is obtained by Ninos plus, and the bound is obtained from UE4 are not compatible with the required large mix. So relatively large. It is still small, but relatively large mixing angle required to explain the LSND and mini-Boon signal here.
Okay, I see. So let's check. No, okay. Just to remind to the people in YouTube that you can write more questions for Christoph. So let's say, is there any other question here in the audience? Because I still have some questions to address to Christoph. So anyway, I can just a very another not. I mean, in the sense, usually most of the experiment is just taking different target, like not target, objective like neutrino or anti-neutrino, and then combining, assuming that the two sectors are completely equal. Is any separated analysis between the two? I mean, that assuming that neutrino and anti-neutrino behave differently, and then the fits are maybe not compatible because they have different mixing angles. Just a very naive question.
So so you see that the reactor anomaly is using antineutrinos, and the gallium anomaly is using neutrinos. So you see that here, the best fits differ, but there's still a significant overlap. And in the case of mini-Boon and LSND, LSND was using only antineutrinos. So this is coming from antineutrinos. And mini-Boon has made a combined analysis of neutrino and antineutrino data. And they see a large excess in the neutrino sample and a smaller excess, but there is still an excess in the antineutrino sample. And in the case of, for example, for these experiments here, so you see the most significant ones are probably the Ninos and Ice Cube. Ninos was running most of the time in neutrino mode, and Ninos plus was, and then the extension Ninos plus, if I remember correctly, was running only in neutrino mode. And for the atmospheric neutrinos and Ice Cube, you cannot distinguish the neutrinos from antineutrinos.
Okay, I see. I have there are other questions here from Martin and Joel. They're asking, okay, 3+1 is not longer acceptable, but how does it compare with 3+0, or is there any hopes for 3+2?
Okay, but this tension cannot go away if you just add more neutrinos, right? Because they are requiring the same mass, the same mass difference, right? So if you had the preferred region, which was sitting here, and the preferred region, which was sitting, for example, up here, then you would need the 3+2 model. But now adding to this here, the 3+ and a fifth neutrino would not help. And what was the first part of the question? Sorry.
Is the 3+1 is not longer acceptable? How does it compare with 3+0? So which is, I guess, give a better fit, 3+1 or 3+0 in the.
No, I mean, so 3+0 cannot fit the mini-Boon LSND signal. And also in the case of 3+0, this is where you have the anti-neutrino anomaly from now. So this is how we try to explain this. So 3+0 will not fit anything of LSND mini-Boon or of the anomalies.
Mm-hmm. So yeah, there is another comment that he said, commenting also, but neither 3+1. So kind of, if 3+0 and 3+1 cannot fit the data, so there is both they have tensions in their own way and their own strength, let's say.
Yes.
Kind of, yeah. So the other question that because you presented in the beginning that everything was, is condensing in this global fit. So can you comment more or less how the global fits are created? Like taking each experiment separated and then combine all the in a super
Yes,
mega chi-square, or each chi-square
yes,
is?
they are. So in order to make this global fit, you first have to reproduce the official analysis from the experiments. So then you can make chi-square calculations, combining them in terms of chi-square. So in this way you take into account correlations which can appear among different oscillation parameters. And so the data, the plot that I have shown here at the beginning is simplified, right? So because I have shown you here the projection, for example, of T2K and nova into this plane. But actually, when we make the analysis of T2K and nova, we also include theta 1,3, and here I didn't show you any plot of the CP phase. Okay. So actually the sectors here, they talk to each other, and this has to be taken into account when making the global fit.
Mm-hmm. So yeah, regarding all these experiments, which are the future experiment that they can deal better with this anomaly? If Dune is for instance better for, or it's gonna be another besides Dune?
Yes, so basically the remaining unknowns that I was saying, like the octant mass ordering or the CP phase, this will be addressed by the next generation of experiments. So I mean, right now we still have like a couple of years of T2K and nova running time. No? Nova will be running until Dune will take over. And T2K, I think it has been approved for an upgrade to this T2K2 or so. I don't remember exactly what the name. But yes, so the T2K and then the future upgrades of the T2K experiment, once Hyper-K is built, they will extract the value of the CP phase with a very good precision, if no new physics scenarios are present. They will also measure the neutrino mass ordering individually at 5 sigma confidence. I think even for the worst case scenario of oscillation parameters, Dune expects to measure the mass ordering at 5 sigma confidence level after 1 year of data taking in the worst case scenario. But this will be like 2030, right? So
yeah, it's gonna be a lot of time to wait that result. So yeah, this is now that you were telling me that, I also I remembered one of the questions that I wanted to do it in the beginning. What about in this? I mean, it's not part of the analysis, or not the typical kind of hypothesis that is included for oscillation neutrinos with the sterile neutrino, but is there any hope to, I mean, or any way to alleviate this tension via non-standard interaction, or I don't know, sacred interaction in between the sterile neutrino sector and the active neutrino sector, or something like that?
I mean, I'm not sure, because I mean, probably there should be some more some way to do this. But you see that there's the bound on U4 here, that the most important contribution comes from Ninos. And in the case of Ninos, the meta effects are not so important. So the NSI have not a large effect in the Ninos analysis. So you can probably alleviate the effect from ice cube or from the atmospheric experiments, but I don't know if you can get rid of Ninos.
So let's say that it's basically oscillation in vacuum, but I mean, the anomaly appears in oscillation in vacuum, let's say.
I mean, it is not completely in vacuum, because it's like 700 kilometer baseline, but the P mu mu channel is in general not so sensitive to meta effects as the P mu E channel would be.
Ah, okay, I understand. Understood. Right. So let's see. Okay, no, in YouTube we don't have any further questions. So I don't know if the very last question from the audience. Oh, okay. So it's just, even though this is not the, I mean, because I remember there were some works in which they were including also the cosmological input from the neutrinos, kind of from the early universe, and
Yes.
but this doesn't modify anything of the tension with the.
Yes. No, yeah, no. If you include cosmology, nothing is allowed. So, so if you look, the red lines here are the ones that I showed you at the beginning from the combined analysis of Meos and Dansk when they were still preferring the 3+1 mixing, right? But you see that actually in this case they require a value of n effective which is larger than 3.9.
Yeah. Yeah. Okay. Yeah. Because maybe there were some, I don't remember well now, but it was related. Yeah,
But
maybe with an ineffective, but those are ineffective that are that principle kind of thermal ineffective, because
no, so this is assuming standard cosmology. You can relax this by introducing secret interactions in your cosmology, and then this bound is relaxed. But I don't know how this works or how this how much this improves the situation.
yeah, right. Okay, so if no other question, so we can thank Christoph. It was very interesting and very nice to see all the improvement that the sterile neutrino research area have arrived to this moment. So let's for the other people that is following law physics, you can check all calendar of webinars that in more or less in 2 weeks more we are going to have another webinar. And of course, thank Christoph for your nice webinar, and for all the people that is following law physics, we see each other in a next time. Bye.